Alright students, it's time to look at Section 3, which is the fossil record. And we're going to start with how fossils form. It's the first little subsection on page 156, book C. Of course, a fossil usually forms when it's buried in sediment. So that means this thing died probably in the water, or is wound up in the water. And as the water carries sediment, which we'll learn a lot more about later, the thing gets buried up, which protects it from things that would eat its remains, and that will let it be preserved. Now, we got three main types. We got your petrified fossil. Petra means rock, so a petrified fossil has turned to rock because minerals soak in, the same minerals that will make stains in your bathtub or your bathroom, especially if you have well water. Those will soak into the organism, plant or animal, and fossilize it when they crystallize and turn back into their rock-like form. Then we'll have molds and casts. A mold is basically like a hole, kind of rhymes too, so hopefully it'll help you remember it, where maybe you pressed your hand into sand. Then you remove your hand, and what's left is, of course, our mold. Now, you may have, as a child, found an animal track and poured plaster of Paris in it. A cast is a copy made from a mold. So it's got the shape of the original organism, but it's not the original organism. It's some sort of mud that got into the hole that was left by the mold. Let's see. Go ahead and finish this up here. So that creature is an exact copy, just like if you have ice cubes in the ice tray is the mold, the cast is the ice. And then finally we got preserved remains. Not too much to say about these, but usually the organism is preserved intact. So we find sometimes pygmy horse and mammoth and things like that, and even ancient humans frozen in the ice. And occasionally we find insects, and maybe we'll even find a small creature trapped in amber. And sometimes we find fairly well preserved remains in the tar pits. So those are our three types of fossils: petrified, molds, casts, and preserved remains. Now as we move on, oops, get us a different sheet there. We look at determining a fossil's age. The first way we can do that is relative dating. Now relative dating does not give an exact age. Does not give exact age. What relative dating means is age is estimated based on the layers that two fossils are found in. Of course, deeper fossils are older, shallower fossils in the rock are, of course, younger. So, age is estimated based on the layers they're found in, so we'll know that one is older than the other, but we won't know any exact ages. That says other. It's getting kind of sloppy there. I'm going to go to a new page for radioactive dating. This gives us nice, firm amounts of time that these organisms may have existed. Radioactive dating is based on the principle of a half-life. Radioactive elements have a half-life. It's the amount of time for half of a substance to decay. So if we start with, say, 1 gram of a substance that has a half-life of 2 years, 2 years later, there's only a half gram of that substance that we want, and then the other half gram has turned into something else. Could be poisonous, could be harmless, hard to say. And this could, of course, be a medicine bottle or some pesticide or something like that. And in 2 more years, this is only a 1/4 gram left. 2 more years after that, we'll only have an 1/8 left. So if we're expecting 1 full gram, and we only find 1/8 of a gram, that tells us that we've had 1, 2, 3 half-lives pass by. And in this example, since a half-life is 2 years, that means 6 years had passed, since we're expecting this amount, but only find this amount. And that's how radioactive dating works. Of course, we'll use different elements for different ranges of dating. We'll use carbon for things in the human timeline because it's good for recent stuff, but we'll use things like potassium and argon to date very, very, very old things. So this is a very important idea, and it lets us date either the animal or the plant or the layer of rock and the materials in it, so that we find animals in that same layer, we know they're the same age as the layer. Now, we'll look at what fossils reveal. Of course, fossils show us extinct organisms. So we see animals that lived long ago but no longer exist. And of course we know that happens because otherwise we'd still have dinosaurs running around. So fossils show us the extinct organisms. And of course it shows us organisms that were similar to current ones but are gone extinct because they didn't change. Now the old ones are still in the fossil record, and we'll see their changed forms still living today. Now we're going to look at the geologic time scale. And this is all of Earth's history. And all of Earth's history is estimated to be about 4.6 billion with a B years long. That is a long, long time. A billion, of course, is 1,000 million years. So hopefully that puts it in kind of a perspective that makes sense to you. We start with pre-Cambrian time, also known as the Precambrian, and this is about 4 billion years long. And not much happened. Or rather, I should say, not much is known, because it's hard to find information on things this long ago, and the first organisms that existed in the Precambrian were squishy. And squishy means you do not get good fossils. So we do not have a good record of most of the organisms at this time, because jellyfish and worms and things like that do not preserve very well because they are squishy. Then the remaining time after Precambrian is divided into eras. An era would be like a year, and then each era is divided into many periods, which is kind of like a month out of a year. So we've got a big division and smaller divisions, and then we won't talk about the subdivisions of that because it gets pretty tedious. But we have the Paleozoic, which means ancient life, Mesozoic, which means middle life, and the Cenozoic, which is where we are now, the age of mammals, which is modern life. Now as we move on, we got a couple unanswered questions. And the first is mass extinction. We know that mass extinctions occur without a doubt because it's in the fossil record. Lots of animals used to live but no longer live, but they could have been caused by a couple different things. Now we know climate change was the key, but what caused that climate change? So we gotta wonder, was it an asteroid, series of volcanoes, or something else? Several unanswered questions there. And of course we've got one more little bit. Another unanswered question is rate of evolution. Now we know evolution is occurring, lots and lots of evidence suggests that, but the rate at which it occurs is still unknown. So we have gradualism, and this is kind of Darwin's thought, is a slow and steady rate of change. We see changes occurring throughout the fossil record, but sometimes we see big jumps in the fossil record, which kind of shows that it's not always slow and steady. Gradualism suggests it's always the same speed, but we have some evidence that suggests that's not the case. And if you think about it, you could probably consider that it's not the case too, because different environments require different rates of change. Then we'll have punctuated equilibria. I'll describe what that means here in a second. Punctuated equilibria means breaking up the balance. Equilibrium is when there is a balance between the organism and its environment. So an organism that is balanced is not going to change much. So at equilibrium, we slow the rate of change. So it's not going to totally stop. It'll switch to more of a gradualism. But then the climate may change, which punctuates or breaks up the balance. When we break the balance, organisms have to change fast to meet the new pressures. So it changes our rate of evolution when the environment changes. And this is probably a more likely situation that seems to be supported by the fossil record as well. So that wraps up Section 3, which is the last section. Remember to look over the outlines of all 3 sections, and of course on page 164, the key points and the terms you should know will be there too. So let's be ready for our test coming up, and good luck.